The adage holds that lightning refrains from striking the same location twice, barring the intervention of someone manipulating the weather. Over a span of 8 years, our solar system has been honored by the presence of 3 extraordinary visitors. These include the perplexing Oumuamua, the conventional Borisov, and presently the cryptic 3 Atlas, notable for its unfamiliar chemistry. These celestial envoys are making their appearance precisely as our technological capabilities advance sufficiently to investigate them with due diligence. This occurrence represents either the most fortunate coincidence in the annals of humanity or a demonstration of patience that extends across geological epochs. Yet what if 3 Atlas is not merely passing through? What if it was constructed for this very moment? Its chemical makeup appears engineered for longevity, its trajectory calculated for inconspicuousness. Considering the latest findings, the pertinent query might not be if extraterrestrials exist, but if they have mastered the art of masquerading as comets. Prepare yourself as we attempt to decipher whether 3 Atlas was shaped by the laws of physics or by a force far more deliberate. Part 1. The inquiry we ought not to pose. On July 1, 2025, an automated telescope located in Hawaii recorded an object that defied conventional existence. It was neither a star nor a planet. It was an entity traversing our solar system at a velocity of 61 kilometers per second, a speed sufficient to break free from the Sun's gravitational hold completely. This object is 3 Atlas, the 3rd verified interstellar body ever identified. The I in its designation signifies interstellar, labeling it as a traveler from outside our local cosmic vicinity. But here is the thought that sends a shiver down your spine. What if its presence was not a mere visit? What if it was dispatched? Now, before you dismiss this notion as mere science fiction, reflect on this point. We are not contemplating whether diminutive green beings are at the helm of a starship navigating our solar system. We are participating in a far more refined exercise, a methodical thought experiment concerning the intent behind an interstellar traveler. When we use the term designed, we are considering a broad spectrum of possibilities. This could be a probe engineered to collect data regarding our solar system. It might be a beacon transmitting information across the vastness of space. It is conceivable that it is a seed transporting the essential components of life between stellar systems. Or perhaps it is nothing more than a relic, ancient technology from a civilization that disappeared millennia ago, continuing its journey through space like a message in a bottle. Let us first outline what we factually understand about 3 Atlas. It was identified by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network of telescopes created to detect objects that could pose a threat to Earth. The 3I label indicates it is the 3rd interstellar object we have confirmed, subsequent to 1I Oumuamua in 2017 and 2I Borisov in 2019. What makes its interstellar nature irrefutable? The mathematics are unequivocal. This object traces a pronouncedly hyperbolic orbit with an eccentricity of approximately 6.08. In the field of celestial mechanics, any value exceeding 1.0 signifies that it is not gravitationally bound to our Sun. It is merely in transit. Its velocity at infinity, the speed it would sustain if the Sun's gravity were to suddenly cease, is recorded at between 57 to 61 kilometers per second. For context, comets originating within our solar system seldom surpass 42 kilometers per second, even when descending from the far-off Oort cloud. Where is this cosmic traveler headed? On October 30, 2025, it is set to achieve perihelion, its nearest pass to the Sun, at a distance of about 1.4 astronomical units. This position is just within the orbit of Mars. Earth will be secure, fortunately, as 3 Atlas will not come closer than 1.6 to 1.8 astronomical units from our world. There is no risk of impact, yet it is close enough for our most advanced telescopes to examine it in unprecedented detail. This is where the situation becomes compelling. Current estimates on its size put an upper boundary on 3 Atlas at 5.6 kilometers in diameter, although it could be as diminutive as 320 meters. The Hubble Space Telescope imaged it on July 21, 2025, and uncovered something extraordinary: a discernible coma, that indistinct envelope of gas and dust, along with a dust plume warmed by the sun. This is cometary behavior, precisely what one would anticipate from a body of ancient ice and rock as it meets solar radiation. However, the chemistry presents a contrasting narrative. On August 25, 2025, the James Webb Space Telescope directed its infrared sensors at 3 Atlas and discovered something atypical. The coma is predominantly composed of carbon dioxide, CO2, with a ratio to water of roughly 8:1. The majority of comets within our solar system display the inverse, where water is the dominant component and carbon dioxide has a secondary role. Even more fascinating, this CO2 enhancement seems more pronounced on the sunward side, as if it is reacting to solar heating in a manner that suggests formation near a CO2 ice line in a remote stellar system. Our window for observation is both valuable and brief. Ground-based telescopes are able to monitor 3 Atlas with clarity until September 2025, after which it will be lost in the sun's glare. It will not become visible again for further observation until December 2025, affording us only brief periods to unravel its secrets. At this point, let us define the parameters for this inquiry. We are not here to assert truths based on speculation. We are examining hypotheses of an engineered object in parallel with the conventional comet model, rigorously distinguishing between factual data and deductive reasoning, and between reasoning and pure imagination. We will triangulate our analysis using the known anomalies of Oumuamua, the atypical chemistry of Borisov, and now the geometry and volatile composition of 3I Atlas. Subsequently, we will overlay established techno-signature frameworks, the scientific methodologies that researchers such as Abraham Loeb and James Benford have formulated to differentiate artificial objects from natural ones. Uncertainty is a perpetual factor in this endeavor. As of this recording, we are still months from its perihelion, so some of our assertions are provisional. We will explicitly label speculative points and reference only verified facts, revising our comprehension as new peer-reviewed findings are published. Yet this is the essential point. Even posing the question, what if it was engineered, compels us to scrutinize 3 Atlas from a new vantage point. It obliges us to contemplate what indicators of intelligence might resemble when concealed as natural occurrences. It challenges us to adopt the mindset of forensic scientists, not merely astronomers. What if, just what if, we are not alone? And what if the proof has been cruising past us at 61 kilometers per second, cloaked in the ideal disguise of a soiled snowball from the stars? The universe, it would appear, still holds secrets it is willing to impart. The question remains, are we attentive enough to comprehend them? Part 2. A Cosmos of Creators. Before we can identify artificial construction, we must first develop an appreciation for nature's own skill in architecture. The universe itself stands as the ultimate creator, shaping complexity out of chaos over billions of years. Stars fashion heavy elements by means of nuclear fusion, converting hydrogen into helium and then into carbon, oxygen, silicon, and iron within their cores. When these celestial forges use up their fuel and detonate as supernovae, they distribute their handiwork across the cosmos. Calcium for our bones, iron for our blood, oxygen for our breath. We are, in a very real sense, composed of stellar material. Gravity acts as the cosmic artisan, molding galaxies through mergers and acquisitions. Dark matter supplies the unseen framework upon which ordinary matter gathers, giving rise to the cosmic web, immense strands of gas and stars divided by apparently vacant expanses. What seems disorderly from our restricted viewpoint shows elegant organization when observed on cosmic scales. Clusters of galaxies drift along these strands like pearls on unseen threads, adhering to patterns set by physics, not deliberate design. This phenomenon persists on more modest scales. Planetary systems form from rotating disks of dust and gas encircling young stars. Terrestrial planets take shape closer to their host stars, whereas gas giants materialize in the more distant regions where water and other substances solidify into icy particles. Life itself could be nature's magnum opus of engineering, self-copying chemical systems that arise from a primordial mixture, evolving to greater complexity via natural selection. The objective here is not to understate the marvel of natural phenomena, but to acknowledge their intricacy. If undirected physical laws can produce such elaborate structures, from the double helix of DNA to the spiral arms of galaxies, then intelligence may learn to replicate these very processes. A highly developed civilization could construct devices that leverage the same physical principles that nature employs, yielding artifacts that seem entirely natural to a cursory glance. Take into account biomimicry, a practice human engineers already utilize widely. Velcro is inspired by the hooks of burr seeds. Sonar technology is based on echolocation in bats and dolphins. Aircraft wing designs are modeled after bird feathers and insect wings. Japanese bullet trains took on the aerodynamic beak form of kingfisher birds to diminish air resistance. If we are capable of emulating nature's designs with our rudimentary technology, one can only imagine what civilizations millions of years more advanced could achieve. They could construct spacecraft that utilize radiation pressure like solar sails, yet disguise this method of propulsion as natural outgassing. They could create probes that employ gravitational slingshot maneuvers around planets and stars, causing their trajectories to resemble the erratic orbits of wayward asteroids. Most ingeniously, they could assemble vehicles that resemble comets, complete with icy shells that sublimate under stellar heat, generating natural-looking tails while hiding advanced instruments inside. Comets serve as especially appealing platforms for camouflage. They are plentiful throughout the galaxy, with trillions thought to exist in our Oort cloud alone. They are self-cooling through sublimation, which provides inherent thermal regulation for sensitive electronics. They are abundant in volatile substances like water, carbon dioxide, and carbon monoxide, compounds that could fulfill a dual role as both propellant and concealment. The dust and gas within cometary comas can effectively mask thermal signatures from infrared telescopes, while also scattering light in a manner that conceals surface features. This leads us into a compelling domain for technosignature investigation. It is possible that advanced civilizations have progressed beyond the basic metal rockets and radio transmissions that define our current technology. Rather than opposing natural forces, they may have learned to collaborate with them. Their artifacts might harness ambient physics so skillfully that they become indistinguishable from astronomical phenomena. We can conceive of several classes of such objects. Inscribed matter probes could transport information encoded directly within their atomic makeup, messages written in isotope ratios or crystalline arrangements that would endure for millions of years. Lurker probes could situate themselves in gravitationally stable areas like Lagrange points, monitoring planetary systems for long durations while appearing as just another asteroid. Stealth reconnaissance vehicles could imitate comets, using their natural comas to conceal sophisticated sensor arrays. The range of hypotheses is extensive, from straightforward mechanical devices to exotic technologies we can hardly imagine. However, we must adhere to rigorous evidentiary criteria. We are not searching for faces on Mars or alignments of pyramids. We require reproducible, measurable signatures that deviate from well-understood natural phenomena in statistically meaningful ways. This brings us to 3 Atlas as a case in point. How do its chemistry, velocity, and geometry align with the catalog of natural occurrences? And, more crucially, Where might it diverge? Its carbon dioxide-rich makeup is atypical, but not without precedent among comets. Its hyperbolic trajectory unequivocally identifies it as interstellar, but the same is true for the orbits of natural debris ejected from other stellar systems. The elegance of this methodology is in its verifiability. If 3I Atlas is merely a natural comet from another star system, its behavior ought to align with physical models derived from studying thousands of comets in our own solar system. Any substantial deviations would necessitate an explanation, either through newly discovered natural processes or potentially through artificial origins. Nature has already demonstrated that the universe is far more bizarre and magnificent than our imaginations could have envisioned. From quantum mechanics to general relativity, from extremophile bacteria to dark matter, reality consistently surpasses our forecasts. Perhaps the highest tribute we could pay to hypothetical alien engineers is to presume they have learned to collaborate with these same natural forces that have molded the cosmos for nearly 14 billion years. The universe is already teeming with architects. The question is whether some of them are conscious. Part 3. Anatomy of an Artifact. Analyzing 3 Atlas from an engineering standpoint, let us examine 3 Atlas as forensic scientists would scrutinize evidence. Each measurement contributes to the narrative. Each observation offers a clue. If this object were engineered instead of natural, those clues ought to be discernible, subtle patterns that diverge from the randomness of cosmic detritus. Let us begin with its geometry. 3 Atlas traces a nearly retrograde orbit, inclined at approximately 156 degrees relative to the plane of our solar system. This severe inclination, in conjunction with its hyperbolic eccentricity of 6.08, leaves no room for doubt regarding its interstellar origin. Natural objects can certainly attain such trajectories through gravitational interactions within their native systems or from encounters during their interstellar journeys. The velocity at infinity, between 57 and 61 kilometers per second, is well within the expected range for objects expelled from other stellar systems. But this is where an engineer's viewpoint becomes compelling. That trajectory positions 3 Atlas close enough to our Sun for thorough observation without nearing Earth. If this were a reconnaissance operation, it reflects either suboptimal targeting or superior stealth, near enough to collect data about our solar system's magnetic field and solar wind conditions, yet distant enough to avoid setting off planetary defense alarms. The brightness profile contributes another dimension to the story. Initial imaging showed a compact coma with a sun-warmed dust plume extending away from the Sun. This is precisely what one would anticipate from a comet meeting increasing solar radiation. Observations from the Hubble Space Telescope on July 21st captured what seems to be the start of a tail forming. Thus far, there is nothing unusual for a comet at 3.3 astronomical units from the Sun. Size estimates limit the nucleus to less than 5.6 kilometers in diameter, and it could be as small as a few hundred meters. The nucleus itself is still not resolved even by our most powerful telescopes, concealed within its expanding coma of gas and dust. For context, Halley's Comet is about 15 kilometers wide, while the renowned Hale-Bopp was nearly 60 kilometers across. 3A Atlas is on the smaller side for comets, though still large enough to remain active over multiple orbits if it were gravitationally bound to our Sun. The chemistry uncovers the most fascinating aspects. Observations from the James Webb Space Telescope indicate a coma dominated by carbon dioxide, with a CO2 to water ratio of roughly 8:1. This is truly out of the ordinary. Most comets in our solar system exhibit the opposite pattern, with water ice being dominant and carbon dioxide playing a secondary role. Even more peculiar, this CO2 enhancement seems most pronounced on the sunward side, implying selective heating or exposure patterns. Natural precedents do exist. Comet 2I Borisov displayed unusually high concentrations of carbon monoxide, suggesting it formed in extremely frigid areas of its home stellar system. Some comets within our own system, such as C2016 R2, Pan-STARRS, have shown a dominance of CO and CO2 over water. But the ratios are significant. The particular composition of 3I Atlas could provide insights into temperature gradients and chemical processes in its place of origin. Now, let us apply an engineer's perspective, purely for speculation. Could this controlled shedding of dust and gas be imitating natural fragmentation while hiding artificial activities? Consider a probe designed to resemble a comet, with an outer shell of ice and dust enclosing sophisticated instruments. As solar heating intensifies, the shell would sublimate naturally, forming the expected coma and tail, while possibly exposing or activating internal systems. What kind of information might such a disguised probe gather during its pass at perihelion? Solar wind composition and magnetic field strength, cosmic ray flux and interplanetary dust density, the gravitational pull of planetary bodies. Essentially, a thorough survey of our solar system's physical environment. This information would be invaluable for any civilization contemplating future visits or colonization. But here is the essential reality check. Based on our current observations, no confirmed fragmentation events have been noted with 3E Atlas. Reports describe normal cometary behavior, coma growth, tail development, and volatile outgassing prompted by solar heating. The object's path shows no indication of course adjustments or artificial propulsion. Its distance from Earth, never less than 1.6 astronomical units, argues against any Earth-focused reconnaissance mission. This serves as a crucial test for the artifact hypothesis. If 3A Atlas were created for Earth observation, its trajectory planning appears remarkably flawed. Unless, of course, the objective was not Earth observation, but rather heliospheric sampling, measuring conditions throughout our solar system instead of concentrating on one specific planet. What observations could disprove claims of an artificial origin? The detection of typical dust and ice grain-size distributions that match natural comet standards would support a natural origin. Isotope ratios that are consistent with stellar nucleosynthesis models would be another powerful indicator. Spectroscopic lines revealing only known ices and minerals with no unusual molecular signatures would point toward natural processes. Conversely, certain findings could bolster the artifact hypothesis. The detection of refined metals or artificial compounds in the coma would be conclusive evidence. Modulated or pulsed emissions not correlated with solar activity could suggest internal power sources or communication systems. Anomalous thermal signatures implying internal heat production could hint at artificial systems. The upcoming perihelion passage provides our greatest chance to collect definitive data. As 3E Atlas nears its closest point to the Sun around October 30, 2025, solar heating will intensify significantly. High-resolution spectroscopy from the James Webb Space Telescope, Keck Observatory, and the Very Large Telescope could reveal the detailed composition of the sublimating materials. Any artificial compounds or unusual isotope ratios should become detectable at this point. Time-variable monitoring could uncover patterns in dust and gas production that do not align with solar heating curves. Natural comets typically show a relatively steady increase in activity as they approach perihelion, driven mainly by rising temperatures and sublimation rates. Artificial objects might exhibit different patterns, such as periodic bursts, asymmetrical jets, or activity that does not follow solar forcing. For now, 3 Atlas remains a captivating natural phenomenon that could be masquerading as something more. Each measurement brings us nearer to comprehending its true identity. Like archaeologists meticulously clearing soil from ancient relics, we are uncovering the secrets of an interstellar visitor, one spectrum at a time. The true beauty is not in verifying our most imaginative speculations, but in the precision of the scientific method itself, our capacity to differentiate between what we wish to find and what nature actually presents. Part 4. Resonances of Oumuamua, the initial signal. To grasp the significance of 3E Atlas, we must first go back to the cosmic enigma that initiated this entire line of inquiry. On October 19, 2017, astronomers identified something without precedent: 1I Oumuamua, the first confirmed interstellar traveler to our solar system. What started as routine asteroid observation swiftly transformed into one of the most fiercely debated scientific discussions of the 21st century. Oumuamua, a Hawaiian term for scout, exhibited behavior that defied our comprehension of natural objects. As it passed the Sun and commenced its departure from our solar system, precise tracking uncovered a non-gravitational acceleration. This phenomenon, in itself, was not extraordinary. Comets commonly undergo such accelerations when jets of sublimating gas generate thrust, akin to miniature rocket engines. But here is what caused scientists unease. No discernible outgassing was observed alongside this acceleration. The Spitzer Space Telescope, designed for infrared observations that should readily pick up the warm dust typically linked to cometary activity, detected nothing. There was no carbon dioxide, no carbon monoxide, no water vapor, none of the usual substances that propel comet jets. Nevertheless, some force was pushing Oumuamua faster than gravity alone could explain. This anomaly led to a proliferation of unconventional theories. The hydrogen iceberg model suggested that Oumuamua was mainly composed of molecular hydrogen ice, which would sublimate without being visible as it neared the Sun. The nitrogen iceberg hypothesis proposed it was a piece of a Pluto-like crust, abundant in frozen nitrogen, which would also sublimate without visible traces. Other theories suggested it was a loosely bound collection of dust and pebbles, fragile enough that internal gas pressure could induce acceleration without creating obvious plumes. Each of these models encountered difficulties. Hydrogen icebergs are not expected to withstand the radiation environment of interstellar space for millions of years. Nitrogen icebergs would necessitate improbably large parent bodies, similar to Pluto. Dust aggregates ought to produce detectable thermal emissions, which Spitzer failed to observe. Then came Abraham Loeb and Shmuel Bialy with their 2018 paper, which proposed that Oumuamua's acceleration could be accounted for by radiation pressure on an exceptionally thin, lightweight object, essentially a natural light sail or a piece of debris from an artificial one. This hypothesis was wonderfully testable. Objects with the appropriate mass-to-area ratio would experience precisely the observed acceleration solely from solar radiation pressure, with no need for mysterious invisible gases. The scientific community's reaction was immediate and predominantly critical. Extraordinary claims demand extraordinary proof, and the radiation pressure hypothesis rested on several assumptions that seemed unlikely for natural objects. How could nature produce such thin, rigid structures? How would they endure interstellar travel without breaking apart? Why was Oumuamua tumbling in such an unusual manner if it were sheet-like? But this is why Oumuamua is crucial for our examination of 3E Atlas. It broadened the scope of what is considered an acceptable anomaly. Before 2017, interstellar visitors were purely theoretical. Now we are aware that they are real, they are detectable, and they can exhibit unexpected behavior that challenges our models of natural phenomena. We must, however, be wary of seeing patterns where none exist. Two data points do not form a trend, particularly when those points are so distinct. Oumuamua showed no detectable volatiles and an unusual acceleration. 2I Borisov, discovered in 2019, acted like a classic comet, with plentiful carbon monoxide and normal outgassing. Now, 3E Atlas offers yet another variation, a carbon dioxide-rich chemistry that is uncommon but not unheard of among comets. This variety actually works against the idea of a single design for interstellar artifacts. If extraterrestrials were dispatching probes to our solar system, one might anticipate some uniformity in their design principles. Instead, we are observing a diversity that points to natural origins from various stellar systems with different formation conditions. The comparison becomes more intriguing when we factor in observational selection biases. Our current survey systems, Pan-STARRS, Atlas, Catalina Sky Survey, Linear, are only capable of detecting relatively luminous objects. We are merely sampling the tip of a massive iceberg, seeing only the largest or most reflective interstellar debris. The Vera Rubin Observatory, set to become operational soon, will significantly increase detection rates and show whether the apparent variety of interstellar objects persists or if patterns begin to emerge with larger sample sizes. What would genuinely designed echoes look like across multiple objects? They would be shared, non-random characteristics that could not result from natural formation processes, such as similar unusual volatile compositions, comparable spin rates or thermal properties, or trajectories that group around specific areas of the sky or show signs of course adjustments. Current laboratory analyses of 3I Atlas's spectroscopy do not reveal any such patterns. Its dominance of carbon dioxide is markedly different from Borisov's abundance of carbon monoxide and Oumuamua's apparent absence of volatiles. If anything, this chemical diversity reinforces the hypothesis that we are observing natural debris from multiple stellar systems with varying formation environments. Nevertheless, we should not completely write off the artifact hypothesis. Advanced engineering might intentionally create diversity to evade detection patterns, or we could be witnessing different categories of objects, some natural, some artificial, mixed in ways that our current observations cannot differentiate. Consider it a large-scale psychological experiment. If the universe were attempting to capture our attention, a series of unusual visitors might be stimuli intended to elicit a response. 3 anomalous objects in 8 years could be a coincidence, or it could be the initial notes of a more extensive message. The Vera Rubin Observatory will help resolve this question by dramatically boosting our detection rate of interstellar objects over the coming decade. For now, 3 Atlas provides our best opportunity to date to spectroscopically analyze an interstellar visitor before it reaches perihelion. Unlike Oumuamua, which was found only after its closest approach to the Sun, we have months to schedule detailed observations of 3 Atlas as solar heating intensifies its activity. The James Webb Space Telescope observations from August 25th are merely the start of this investigation. As 3 Atlas nears perihelion, we will monitor its behavior with unparalleled precision, searching for patterns that differentiate artificial processes from natural ones. Oumuamua gave us the first knock on the door of possibility. 2I Borisov showed us what typical interstellar comets look like. Now, 3I Atlas offers our third data point in this cosmic game of pattern recognition. Whether that pattern ultimately reveals natural diversity or something more profound will be decided by meticulous observation and rigorous analysis. The universe, it appears, is teaching us patience and the importance of keeping our minds open while upholding the highest standards of evidence. Part 5. The Dark Forest Parallel. Liu Cixin's science fiction trilogy, The Three-Body Problem, acquainted millions of readers with a sobering concept, the dark forest hypothesis. In this paradigm, the universe is akin to a dark forest where every civilization is a hunter moving silently among the trees. This is because making any noise or revealing one's location is an invitation for destruction by other hunters. Survival hinges on silence. But what if survival also necessitates information? This fictional construct, though entirely speculative, provides a valuable framework for assessing interstellar reconnaissance methods. If civilizations are scattered throughout the galaxy but maintain radio silence for protective reasons, how might they acquire intelligence about potentially life-sustaining star systems? Small, deniable artifacts could sample environments without disclosing the sender's location or capabilities. Let us apply this reasoning to 3 Atlas. Its trajectory takes it through our solar system without making a close approach to Earth, never coming nearer than 1.6 astronomical units. If this were a reconnaissance mission, it appears to be poorly planned for Earth-specific observation. But perhaps Earth was never the main objective. Think about the valuable information a disguised probe could collect during a solar system transit. The composition and magnetic field strength of the solar wind would indicate the star's age and activity level. Planetary masses and orbits could be determined through gravitational perturbations. The existence and distribution of dust and debris throughout the system would provide insights into asteroid belt characteristics and comet populations. Most crucially, the probe could sample the heliospheric boundary conditions that would impact future interstellar missions to this system. This type of reconnaissance is strategically sensible on million-year timescales. Galactic civilizations, if they exist, might operate with a level of patience that makes human historical experience seem insignificant. A single probe passing through a star system could collect baseline data for future use, even if no immediate follow-up missions are intended. The cost is minimal, one small expendable object, while the information obtained could be invaluable centuries or millennia later. The elegance of this strategy is its deniability. Objects like 3 Atlas could be written off as natural debris unless detailed analysis uncovered clearly artificial signatures. Even in that case, the probe's origin would remain ambiguous. Was it dispatched by a civilization in Vega, Proxima Centauri, or some undisclosed star system hundreds of light-years away? The sender's identity and location would stay protected. Contrast this with the lurker hypothesis put forth by researchers like James Benford. Lurker probes would situate themselves in gravitationally stable positions, Lagrange points, co-orbital locations with planets, or long-period asteroid-like orbits, where they could monitor target systems for extended durations. These represent a different strategic approach: permanent monitoring stations versus temporary reconnaissance flybys. 3I Atlas does not match the lurker profile. Its hyperbolic trajectory will take it out of our solar system for good, never to come back. This implies either a one-time sampling mission or simply a natural object adhering to the gravitational dynamics that control all interstellar debris. But let's look at the risk assessment from an alien viewpoint. If hostile civilizations truly exist, artifacts designed for maximum ambiguity might be the most secure method for intelligence gathering. A probe that looks exactly like a comet, behaves exactly like a comet, and shows no artificial signatures to casual observation would be practically undetectable to primitive civilizations like our own. The paradox is that 3 Atlas's very visibility contradicts the stealth hypothesis. Its bright coma and tail make it easily observable by ground-based telescopes, attracting precisely the kind of attention a clandestine mission would seek to avoid. Unless, of course, that visibility is a component of the camouflage. What better disguise for sophisticated instruments than the natural spectacle of a sublimating comet? If the intention were to be seen, if the objective were announcement rather than stealth, the trajectory still appears less than ideal. A closer approach to Earth would have ensured more notice from human observers and permitted a more detailed study of our planet's features. Instead, 3 Atlas passes by at a respectful distance, collecting data about our solar system's general characteristics while steering clear of any impression of specific interest in Earth. This analysis highlights a fundamental difficulty in technosignature research, distinguishing between flawed design and deliberate ambiguity. A clearly artificial object would be easy to spot, but might signify a diplomatic or scientific contact attempt rather than covert surveillance. A perfectly camouflaged probe would be, by definition, undetectable. We are searching for objects that exist somewhere between these two poles, artificial enough to be identified with careful analysis, but natural enough to maintain plausible deniability. Current observations of 3E Atlas do not strongly support the reconnaissance hypothesis. Its carbon dioxide-rich chemistry, while unusual, is within the range of natural variation seen among comets. Its coma and tail development follow predictable patterns based on solar heating and volatile sublimation. No overtly artificial signatures have been found in its spectrum or morphology. Yet the dark forest framework serves as a reminder to consider motivations and methods that could be entirely foreign to human experience. We assume that reconnaissance would specifically target Earth, but perhaps the goal is to characterize stellar environments more broadly. We anticipate that artificial objects will betray themselves through technological signatures, but perhaps advanced engineering has learned to operate entirely within the bounds of natural physical processes. The question of how to respond becomes ethically intricate. If we ever do identify genuinely artificial interstellar visitors, should we try to communicate? Should we observe discreetly while maintaining our own defensive silence? Should we disregard such objects entirely to avoid alerting potentially hostile observers to our capabilities? For now, these remain philosophical exercises rather than practical dilemmas, but they refine our observational criteria and remind us that the absence of obvious artificial signatures does not necessarily confirm a natural origin. Sometimes the most effective hiding place is in plain view, disguised as something so common that no one gives it a second look. The universe may indeed be a dark forest, but even hunters occasionally leave behind tracks, and patient observers can sometimes detect the shadows moving among the trees. Part 6. Seeds on the Galactic Breeze. Envision life itself as a cosmic traveler, transported between star systems, not in spacecraft, but aboard comets and asteroids coasting through the interstellar expanse. This idea, known as panspermia, posits that life could propagate throughout the galaxy through natural means, or perhaps with some intentional help. The fundamental concept is not novel. In 1973, Nobel laureate Francis Crick and chemist Leslie Orgel put forward the idea of directed panspermia, the hypothesis that life on Earth might have been initiated by microorganisms deliberately dispatched by an extraterrestrial civilization. This was not speculative science fiction, but a serious scientific proposition that could be tested through biochemical and genetic analysis of Earth's biosphere. Crick and Orgel pointed out several perplexing aspects of terrestrial biology that might lend support to an artificial origin. The genetic code seems to be almost universal across all known life forms, implying a single point of origin rather than multiple independent developments. Certain trace metals, such as molybdenum, play vital roles in terrestrial biochemistry, despite being relatively scarce in Earth's crust. Meanwhile, more common metals like chromium and nickel are largely neglected by biological systems. This pattern could be a reflection of the chemistry of another world where these trace elements were more accessible. Modern research has shown that natural panspermia, or lithopanspermia, is not only feasible but likely unavoidable. Asteroid and comet impacts can eject rocks from planetary surfaces with enough force to escape gravitational pull. Some of these rocks, now journeying through interstellar space, undoubtedly harbor microorganisms within their crystal structures, shielded from radiation and cosmic rays by meters of stone. Comets are especially suitable vehicles for transporting such biological cargo. Their icy composition provides natural refrigeration, keeping temperatures near absolute zero for most of their interstellar voyages. They are rich in organic compounds, carbon-based molecules that are the fundamental components of terrestrial biochemistry. When they encounter stellar radiation, they sublimate gently rather than undergoing the shock heating that might sterilize rocky debris. This brings us to 3E Atlas and its unusual chemistry. The James Webb Space Telescope detected a coma dominated by carbon dioxide with CO2 to water ratios of approximately 8:1. While this composition appears atypical compared to comets in our solar system, it might reflect the formation conditions in a very different stellar environment, perhaps around a star with a different luminosity or in a protoplanetary disk with different temperature gradients. But this is where the speculation becomes intriguing. What if this unusual chemistry is not merely revealing the formation environment, but actually serves as a preservation medium for complex organic molecules? Carbon dioxide is an excellent protective matrix for biological materials, maintaining stable low temperatures while offering chemical buffering against radiation damage. If one were to design a long-term preservation system for biological samples, one might opt for precisely this type of chemical environment. The library in ice concept takes this logic a step further. Instead of transporting living organisms, interstellar comets could carry information, genetic codes, biochemical instructions, or even digital data encoded in crystalline matrices. Such information could endure for millions of years in the cold vacuum of interstellar space, effectively creating a galactic backup system for biological and technological knowledge. This method has significant advantages over radio transmission. Electromagnetic signals weaken with distance and can be disrupted by stellar interference. Physical media, if properly shielded, can carry vastly more information with perfect fidelity over arbitrarily long distances. A single comet-sized object could transport the equivalent of Earth's entire digital library while appearing completely natural to a casual observer. It is time for a reality check. No instrument has yet detected biological materials or anomalous organic compounds in 3E Atlas. The upcoming perihelion observations from the James Webb and ground-based telescopes could significantly tighten these constraints as solar heating leads to increasingly vigorous outgassing. Any complex organic molecules should become detectable through spectroscopic analysis. Let us compare 3E Atlas to its predecessor, 2I Borisov, which showed an abundance of carbon monoxide, implying it formed in extremely cold regions of its parent stellar system. This chemical signature supported natural formation scenarios while also revealing the diversity of protoplanetary disk environments throughout the galaxy. 3E Atlas's carbon dioxide signature might tell a similar story about temperature gradients and chemical processes in some distant stellar nursery. The delivery problem poses another challenge to directed panspermia scenarios involving 3I Atlas. Its closest approach to Earth will be more than 1.6 astronomical units, far too distant for any kind of biological seeding mission. Even if it were carrying living organisms or genetic material, that cargo would continue past us into the outer solar system and eventually back into interstellar space. But perhaps precise targeting was never the objective. Instead of aiming for specific worlds, the directed panspermia hypothesis might envision a galactic drift seeding strategy. Billions of seed-carrying comets, launched over millions of years, scattered throughout the galaxy with no particular targets. Statistical mechanics would ensure that a certain fraction eventually encounters suitable planetary systems, while the vast majority continues to wander through space indefinitely. This approach is similar to strategies already seen in terrestrial biology. Dandelion seeds do not aim for specific patches of soil. They are released in vast numbers to be carried by wind currents, with success measured in probabilistic terms rather than precision delivery. Spores from fungi and bacteria use similar dispersal methods, colonizing new environments through sheer numbers rather than selective targeting. What observational evidence could support the presence of biological cargo in 3E Atlas? The detection of prebiotic organic compounds, amino acids, nucleotides, lipids, with isotopic ratios different from those in our solar system would be highly suggestive. The discovery of stereoisomer preferences or molecular handedness that match terrestrial biology might point to a common origin. The most compelling evidence would be the detection of clearly biological polymers, proteins, DNA, RNA, that could not have arisen from purely chemical processes. Current spectroscopic capabilities make such detections extremely difficult, but not impossible. As 3 Atlas approaches perihelion and outgassing intensifies, the most sophisticated instruments on Earth will be searching for precisely these kinds of molecular signatures. The philosophical implications go far beyond biology. If life can spread naturally between star systems, then the galaxy might be far more interconnected than we imagine. Rather than isolated islands of evolution, planetary biospheres could be nodes in a vast network of genetic and biochemical exchange, operating on million-year timescales. Whether that network arose purely through natural processes or received some deliberate help remains an open question. But 3 Atlas, with its unusual chemistry and interstellar origin, represents our best current opportunity to search for answers. It carries with it the chemical fingerprints of another world, another time, and possibly, just possibly, another form of life entirely. Even if 3 Atlas turns out to be nothing more than frozen gases and rocky debris from some distant stellar system, it still brings a message. It informs us about the chemistry of worlds we will never visit, the physics of environments we will never experience directly, and the processes that shaped matter in regions of space separated from us by light years and eons. In that sense, every interstellar visitor is already a library, a storehouse of information about cosmic processes and planetary formation. The question is whether some of those libraries were compiled by librarians. Part 7. Alien Engineering 101. Arthur C. Clarke's third law declares that any sufficiently advanced technology is indistinguishable from magic. However, there is a corollary that may be even more pertinent to our inquiry. Any sufficiently advanced technology might be indistinguishable from nature itself. If one's goal were to construct a probe capable of traveling between star systems without being detected, one would design it to leverage the same physical principles that govern natural objects. Let us consider this as an engineering problem. What design specifications would dictate the construction of an interstellar reconnaissance probe? Firstly, it must withstand the journey which could last millions of years in the unforgiving environment of interstellar space, where it would be subjected to bombardment by cosmic rays and micrometeorites. Secondly, it must be able to gather local energy upon arrival, as transporting fuel over such vast distances would be prohibitively costly in terms of mass and volume. Thirdly, it must blend in perfectly with natural debris to evade detection by less advanced civilizations. Fourthly, it should have some capability for self-repair or adaptive response to new conditions. The solution almost designs itself. Construct the probe to resemble a comet. Ice provides natural shielding against radiation, protecting sensitive electronics from cosmic ray damage during the interstellar voyage. Ices of water, carbon dioxide, and carbon monoxide offer excellent thermal buffering, maintaining stable low temperatures that preserve both biological samples and electronic components. These same volatile substances become a source of fuel for maneuvering once the probe encounters stellar radiation. Sublimation creates natural jets that can generate thrust for course adjustments, all while appearing entirely normal to observers. The outer layers of dust and ice fulfill several roles. They scatter sunlight in a way that conceals surface features and thermal signatures. They supply raw materials for self-repair through controlled sublimation and redeposition. Most ingeniously, they produce the spectacular display of coma and tail formation, which diverts attention from the probe's primary functions while seeming to be nothing more than natural cometary activity. Propulsion becomes elegantly straightforward through the biomimicry of celestial mechanics. Utilize gravity assists from planets and stars to modify the trajectory, a method human engineers already use regularly. Harness solar radiation pressure for precise course adjustments, again imitating natural processes that influence all small bodies in stellar systems. Time these maneuvers to coincide with natural outgassing events that would produce similar accelerations in genuine comets. instrumentation could be embedded within the ice matrix, shielded from detection by meters of natural camouflage. Sensors for magnetic fields, particle density, gravitational variations, and electromagnetic radiation could function continuously while appearing to casual observers as nothing more than irregular features in the comet's nucleus. Data storage could make use of the probe's own molecular structure, with information encoded in isotope ratios, crystal orientations, or organic polymer sequences that would last indefinitely in the cold vacuum of space. Communication presents intriguing challenges and possibilities. Conventional radio transmission would risk detection and betray an artificial origin. However, the probe could modulate its natural emissions, altering the composition or timing of its outgassing in ways that encode information. Such signals would seem like natural variations in cometary activity unless observers knew precisely what patterns to search for. Failure modes transform from bugs into features. In this design approach, as the protective ice shell wears away under solar heating, internal systems are revealed. But this process looks exactly like the normal evolution of cometary nuclei as they approach perihelion. Components might be designed to break apart in controlled ways that mimic natural fragmentation events, while also dispersing multiple smaller probes throughout the target system. Power generation could exploit temperature differences between the sun-facing and shadowed sides of the probe, using thermoelectric effects that produce no detectable emissions. Energy storage could utilize phase transitions within the ice matrix itself, effectively turning the entire probe into a battery that charges and discharges through natural heating and cooling cycles. The engineering sophistication of such a system lies in its complete harmony with natural physics. Every artificial component serves multiple purposes while maintaining perfect camouflage. The probe does not struggle against natural forces. It harnesses them, becoming a technological master of Aikido that redirects cosmic energy flows to achieve its objectives. Now, let us apply this speculative framework to 3E Atlas. Its carbon dioxide-rich chemistry could be a sophisticated preservation medium for instruments or biological samples. The sunward enhancement of CO2 emissions detected by the James Webb might signal the selective heating of surfaces designed to activate at specific solar distances. The compact, unresolved nucleus could be concealing complex systems beneath layers of natural ice and dust. But here is the essential discipline. The absence of evidence is not evidence of absence, but it is also not evidence of presence. 3E Atlas has displayed no confirmed signatures that diverge from natural cometary behavior. Its spectral emissions are consistent with known ice sublimation processes. Its trajectory adheres to gravitational dynamics with no obvious course corrections. Its morphology is similar to that of thousands of comets observed in our own solar system. The burden of proof rests squarely on those making extraordinary claims. If 3E Atlas were an artificial probe, we should be able to detect some signature that sets it apart from natural objects, such as modulated emissions, anomalous thermal patterns, unusual grain compositions, or isotopic ratios that do not align with stellar nucleosynthesis models. Our observational wish list for the upcoming perihelion passage includes high-resolution spectroscopy across multiple wavelengths, time-variable monitoring of dust and gas production, polarimetry to characterize grain properties, and thermal imaging to map surface temperature variations. These observations could potentially uncover artificial signatures while simultaneously enhancing our understanding of interstellar comet physics. The comparison with 1I Oumuamua remains enlightening. That object's non-gravitational acceleration without visible outgassing lent some credibility to the hypothesis of an artificial surface, perhaps a light sail-like structure utilizing radiation pressure. However, the engineering interpretation is still debated, with several natural explanations still being considered. This design exercise is valuable regardless of 3E Atlas's true nature. It sharpens our observational criteria, suggests specific tests for distinguishing between artificial and natural phenomena, and reminds us that advanced technology might be far more subtle than our current assumptions imply. Whether 3 Atlas represents advanced alien engineering or simply the fascinating natural physics of interstellar debris, it is teaching us to see the universe with fresh eyes. Sometimes the most profound discoveries come not from confirming our expectations, but from learning to ask better questions about the cosmic mysteries sailing past us at 61 kilometers per second. Part 8. Cosmic Camouflage and the Anti-Tail Illusion. Nature has a fondness for optical illusions, and this is nowhere more evident than in the ethereal spectacles created by comets. A solid grasp of these natural light shows is essential when determining whether unusual morphology could be a sign of artificial origin or simply physics playing tricks on our senses. Let us begin with fundamental comet anatomy. As these icy travelers approach the Sun, solar radiation heats their surfaces, causing frozen volatiles to sublimate into gas that forms the coma, that hazy envelope around the nucleus. The solar wind, a stream of charged particles flowing out from the Sun, pushes ionized gas directly away from our star, creating the ion tail that always points in the antisolar direction, irrespective of the comet's movement. In the meantime, radiation pressure affects dust particles released by the sublimating ice, forming the dust tail, which curves along the comet's orbital path due to the particle's momentum. But occasionally observers notice something that seems to contradict these principles: a sunward spike extending from the comet's head, appearing to point directly towards the Sun instead of away from it. This anti-tail looks so unnatural that early astronomers questioned if they were observing some form of propulsion system. The explanation is purely a matter of geometry. Large dust grains, too heavy to be significantly influenced by radiation pressure, stay close to the comet's orbital plane. When Earth intersects this plane, we are viewing these particles edge on, which creates an optical illusion of material extending towards the Sun. It is the same phenomenon that causes Saturn's rings to look like a thin line when seen from their edge, even though they are thousands of kilometers thick. There are numerous historical examples. Comet Bradfield in 1975 exhibited a spectacular anti-tail that was visible for weeks. Comet Kohoutek displayed similar features in 1973 and 74. More recently, Comet ZTF showed sunward spikes during its 2023 appearance, and Comet C-2023-A3 Tsuchinshan Atlas showed anti-tail features during its 2023 passage. This phenomenon is important for our investigation because it shows how easily natural processes can produce seemingly anomalous morphology. When assessing claims about artificial objects, we must first rule out all natural explanations, even those that initially seem to defy physical intuition. 3 Atlas has already started to show morphological changes consistent with normal comet behavior. Hubble Space Telescope imaging has revealed a teardrop-shaped coma with a sunward-warmed dust plume extending in the antisolar direction. The first signs of tail formation appeared exactly where comet physics predicts, driven by the increasing intensity of solar radiation as the object approaches perihelion. The James Webb Space Telescope observations add another layer of understanding. The sunward enhancement of carbon dioxide emissions corresponds precisely with illumination patterns. The hemisphere facing the Sun receives more energy and therefore exhibits more vigorous outgassing. This behavior follows solar forcing rather than any internal activity cycle, supporting natural rather than artificial explanations. But let us consider what would genuinely be surprising. Periodic dust pulses that are not correlated with solar distance would require an explanation, either through previously unknown natural processes or artificial control systems. Jet activity that remained at a constant intensity, regardless of solar heating, would violate basic thermodynamics. Dust grains with unusual compositions or size distributions might suggest manufacturing rather than natural condensation processes. Even more subtle signatures could indicate an artificial origin. Natural comet jets typically have a turbulent, chaotic structure as they interact with the solar wind and radiation pressure. Artificially controlled jets might display more regular patterns, such as quantized intensity levels, geometric spray angles, or timing synchronized with celestial mechanics in ways that natural processes would not produce. Observational campaigns coordinated across multiple telescopes could potentially detect such anomalies. Simultaneous imaging at different wavelengths might reveal thermal signatures that are inconsistent with purely solar heating. Polarimetry could characterize dust grain properties, distinguishing between naturally condensed particles and potentially manufactured alternatives. Spectroscopy could search for molecular emissions that do not match standard ice sublimation models. The cautionary tale of Comet Ison remains relevant here. This object fragmented dramatically as it approached the Sun in 2013, demonstrating that drastic morphological changes near perihelion are not rare events that require an artificial explanation. Comets are loosely bound collections of ice, dust, and rock that can react unpredictably to thermal stress and tidal forces. Current observations suggest that 3 Atlas remains intact as it approaches its October 30th perihelion passage. But if fragmentation does occur, we must resist the urge to interpret such events as evidence of an artificial origin unless they exhibit patterns that are clearly inconsistent with natural breakup mechanisms. The broader point extends beyond comet morphology to all aspects of anomaly hunting in space. Human pattern recognition evolved to detect meaningful signals in noisy environments, rustling bushes that might hide predators, faces in crowds that might indicate social allies or threats. But this same pattern recognition can produce false positives, seeing intention where only physics is at play. Advanced image processing and statistical analysis can help mitigate these cognitive biases. Machine learning algorithms can identify subtle patterns in spectroscopic data that human observers might miss while avoiding the pareidolia, seeing faces in clouds, that affects visual interpretation. But ultimately, extraordinary claims require extraordinary evidence, and that evidence must be reproducible across multiple independent observations. 3 Atlas continues to look remarkably normal by comet standards, despite its interstellar origin and unusual chemistry. Its anti-tail, if one develops during the upcoming plane-crossing geometry, will almost certainly prove to be the same optical illusion that has misled observers for centuries. Its jets and dust production follow predictable patterns based on solar heating and volatile sublimation. Yet this normalcy should not be a disappointment. Every observation contributes to our understanding of interstellar objects and the diversity of conditions in distant stellar systems. Whether artificial or natural, 3 Atlas is a messenger from another world, carrying information about cosmic processes that we can study in no other way. The universe presents us with natural magic tricks, spectacular enough to evoke wonder without the need for artificial intervention. Sometimes the most profound discoveries arise from understanding how nature creates its illusions, rather than from discovering that wizards truly exist. Part 9. Echoes of Lost Civilizations. Imagine 3 Atlas not as a probe or a messenger, but as something far more melancholic. A relic, a cosmic artifact from a civilization that disappeared eons ago, now drifting through the galaxy like a message in a bottle thrown into a sea of stars. This possibility shifts our investigation from a quest for active intelligence to an endeavor in galactic archaeology. The process for creating such relics is surprisingly ordinary. Planetary formation is a tumultuous process involving gravitational interactions among countless bodies over millions of years. During the late heavy bombardment period that marked the early evolution of stellar systems, massive gravitational perturbations can launch substantial debris into interstellar space. Some of this material might carry the technological artifacts of civilizations that thrived and perished while their home systems were still settling into stable arrangements. Consider our own solar system's turbulent beginnings. Jupiter's migration through the inner solar system likely scattered countless asteroids and comets, sending them on interstellar trajectories. If technological civilizations had existed on early Earth or Mars during this chaotic era, their artifacts might now be journeying between the stars, indistinguishable from natural debris to a casual observer. The lesson from 2I Borisov is relevant here. This clearly natural interstellar comet had a distinctive chemical makeup, with unusually high concentrations of carbon monoxide that revealed the conditions in its birth environment. The CO richness suggested it formed in extremely cold regions of its parent stellar system, perhaps near the CO ice line, where temperatures fell below -200 degrees Celsius. This chemical signature endured through millions of years and light years of interstellar travel. If technological artifacts could survive similar journeys, they might carry equally distinctive signatures, not just of their formation environment, but of the civilizations that produced them. Unusual isotope ratios could indicate nuclear processes unknown in nature. Complex organic polymers could preserve information in molecular form. Even the bulk composition of such objects might reveal industrial processes rather than natural condensation. 3 Atlas provides our first chance to test these possibilities with state-of-the-art spectroscopic analysis. The James Webb Space Telescope's detection of a carbon dioxide-dominated chemistry sets a baseline for comparison with natural processes. As solar heating intensifies during the approach to perihelion, more sophisticated molecular analysis might reveal whether this chemistry reflects natural ice condensation or something more complex. The idea of survival across cosmic timescales should not seem far-fetched. Biological molecules can remain stable for millions of years under the right preservation conditions. DNA has been retrieved from fossils hundreds of thousands of years old. Amino acids are found in meteorites that formed billions of years ago. Technological materials designed for longevity could potentially maintain their structural integrity over even longer periods when shielded by meters of ice in the vacuum of interstellar space. Information storage becomes particularly fascinating in this context. Rather than fragile electronic media that might degrade over geological time, advanced civilizations might encode information directly into atomic and molecular structures. Crystal lattices could preserve digital data through precise arrangements of dopant atoms. Organic polymers might carry genetic or cultural information in sequences similar to DNA. Even isotope ratios could be artificially manipulated to create detectable patterns that convey meaning. The time capsule analogy extends beyond mere information storage to include actual technological components. Imagine a civilization on the brink of extinction, perhaps due to stellar evolution, an asteroid impact, or climate change that deliberately launched preserved samples of their technology into interstellar space, not as an attempt at communication, but as a safeguard against total obliteration. A portion of these technological seeds could eventually be uncovered by other societies, safeguarding knowledge that would otherwise be eternally lost. Existing observations of 3I Atlas lend little credence to this possibility. Its distance from Earth at its nearest point surpasses 1.6 astronomical units, which makes a deliberate delivery of a message to our kind improbable. The object's path points to either random gravitational interactions or perhaps a mission intended to gather data on heliospheric conditions instead of aiming for any specific planet. Yet it is conceivable that precise targeting was never the goal. A society launching technological remnants might adopt the same statistical method employed in biological seed distribution, releasing immense quantities of objects without set destinations and depending on fortuitous encounters over eons to guarantee that some portion eventually finds suitable discoverers. The philosophical implications of this idea reach well beyond the field of astrobiology. Throughout the course of human existence, artifacts have consistently outlived the people who made them. My studies of ancient cultures are conducted mainly through their technological leftovers, such as pottery, tools, buildings, and works of art. These items communicate across centuries and millennia, retaining information about societies that did not leave behind any written documentation. If technological societies emerge and decline across the galaxy on timelines similar to those of stellar evolution, then the space between stars could be strewn with comparable artifacts. A certain percentage of the items we categorize as asteroids, comets, and interstellar matter might in fact be the archaeological vestiges of extinct civilizations. This concept leads to predictions that can be tested. Authentic technological artifacts ought to exhibit material characteristics that set them apart from objects formed by natural means. Their isotopic ratios should differ from the models of stellar nucleosynthesis. Their mineral makeup could contain refined metals or synthetic materials not found in natural formations. Crucially, they might hold information with patterns in their molecular framework that communicate meaning rather than just mirroring the processes of physical and chemical creation. As 3 Atlas moves toward perihelion, progressively more detailed spectroscopic examinations will put these theories to the test. High-resolution observations have the potential to identify the molecular markers that would separate natural ice formation from intentional technological creation. The difficulty is in identifying such markers upon encountering them, as I have no existing examples of alien technology to use for comparison. Even if 3 Atlas turns out to be composed entirely of natural frozen gases and stony fragments from a faraway star system, it still serves as a kind of message from a bygone era. Its chemical makeup holds information about the conditions in its place of origin billions of years ago. Its voyage provides data on interstellar environments and the mechanics of material transfer between star systems. In that respect, each visitor from interstellar space already acts as a time capsule, bringing knowledge about cosmic phenomena that I can investigate in no other manner. The question that propels my inquiry is whether some of those capsules might bear messages that are more than just chemical, carrying the preserved ideas and technologies of minds that once gazed upon the same stars I observe today. In the end, we are all archaeologists at this point, examining the artifacts that wander between the stars and speculating which of them might tell a story, not just of physics, but of intelligence, of momentary flashes of consciousness that shone briefly in the vast cosmic darkness before their memories were scattered on the galactic wind. Part 10. The Surveillance Hypothesis. What if 3 Atlas is not attempting to initiate contact? What if its function is simply to watch, measure, and catalog, representing a cosmic intelligence-gathering mission concealed as an ordinary astronomical event? This surveillance hypothesis redirects the investigation from a search for a greeting to an analysis of its reconnaissance potential. I consider the strategic reasoning from an extraterrestrial viewpoint. Making direct contact with a less advanced civilization entails substantial risks. Cultural contamination could interfere with the natural development of a society. Providing technological advancements might upset established power balances or lead to destructive wars. Even well-intentioned efforts at communication could elicit fear, aggression, or cargo cult-like behaviors that would make future dealings more difficult. However, gathering information poses fewer moral dilemmas. A civilization could acquire all the necessary information about a target system, including stellar properties, planetary makeup, levels of technological progress, and even fundamental cultural traits, without ever making its presence known or meddling with natural evolutionary paths. The trajectory of 3I Atlas presents fascinating scenarios for this type of reconnaissance. Although it will not come closer to Earth than 1.6 astronomical units, this distance positions it securely within the heliosphere, the bubble of solar wind and magnetic fields enveloping our solar system. From this vantage point, an advanced probe could collect samples of conditions that disclose key features of our stellar surroundings. The composition of the solar wind changes with a star's age, the intensity of its magnetic field, and the processes of internal fusion. By examining the density of particles, their energy spectra, and their isotopic ratios in the solar wind, observers could ascertain our Sun's stage of evolution, its remaining lifespan, and its stability. This knowledge would be vital for any civilization contemplating a long-term engagement with our solar system. The magnetic field of the heliosphere contains indicators of solar activity cycles, coronal mass ejections, and other events that impact planetary atmospheres and technological systems. Grasping these patterns would be crucial for scheduling future missions or communication attempts to sidestep periods of intense radiation or magnetic disruption. Gravitational analyses could determine the masses and orbital details of planets across our solar system without needing to get close to any particular world. Minor deviations in a probe's path would signal the existence and rough size of planetary bodies, creating a catalog of potentially life-supporting environments. Even the cosmic ray conditions inside our solar system hold valuable intelligence. The heliosphere acts as a partial barrier against galactic cosmic rays, which results in a distinct radiation environment that influences both biological evolution and technological advancement. Measuring this shielding effect would aid external observers in comprehending the circumstances that have molded life on Earth and that continue to shape our technological progress. From this angle, the fact that 3I Atlas misses Earth becomes an asset rather than a flaw. Getting too close to planets could lead to detection and might provoke defensive actions from cautious civilizations. Keeping a respectful distance while gathering extensive environmental information is a more discreet way of collecting intelligence. The analogy of a spy satellite is quite revealing. Military reconnaissance satellites follow orbits that strike a balance between their observational power and their ability to survive, frequently hiding their real objectives under the guise of scientific missions. Weather satellites, communication relays, and navigation systems all offer dual-use functions for both civilian purposes and military intelligence collection. In a similar vein, a probe disguised as a natural comet could amass a huge amount of scientific and strategic information while ensuring complete operational secrecy. Its brilliant coma and tail would divert focus from any instruments hidden inside its nucleus, and its clearly natural look would ward off any suspicion of an artificial origin. But this is where the surveillance hypothesis runs into major obstacles based on current observations. 3 Atlas has not shown any behavior that strays from the physics of a natural comet. Its chemistry, rich in carbon dioxide, though uncommon, is within the known spectrum of natural diversity. Its outgassing patterns align perfectly with solar heating rather than any internal activity cycles that might hint at artificial mechanisms. Most significantly, no non-thermal emissions have been detected. Natural comets shine by reflecting sunlight and through fluorescence from energized gas molecules. Artificial systems would probably produce noticeable signatures from power generation, data handling, or communication functions. Present spectroscopic studies have yielded no signs of such technological emissions. The observational checks for surveillance capabilities become highly specific. I must look for narrow-band emissions that do not correspond to known molecular transitions. I must search for polarization patterns that are not consistent with the natural scattering of dust. I must monitor for changes over time that align with terrestrial radio signals or space activities rather than with solar influence. Advanced radar could potentially find structured objects hidden within the comet's nucleus, although the limitations of range and signal weakening through the coma make such observations incredibly difficult. Thermal imaging might show temperature patterns that are not in line with heating solely from the sun, which would suggest internal heat sources from power generation or data processing. The comparison with One-Eye Oumuamua is still pertinent here. That object's non-gravitational acceleration without any visible outgassing led to theories about artificial propulsion or surfaces like a light sail. While natural explanations are still being debated, the anomaly showed that interstellar objects can behave in unexpected ways that question our grasp of natural phenomena. 3 Atlas presents a more straightforward test case. Its clear cometary activity offers a natural reason for any changes in its path due to the thrust from outgassing. Its chemical makeup, while distinctive, is consistent with known physical processes of volatile sublimation and gas release. Any artificial markers would have to be found against this backdrop of typical comet behavior. A risk assessment from a human standpoint would advise treating ambiguous objects as scientific chances rather than as security risks. At its current distance and with the current probabilities of interaction, 3 Atlas presents no conceivable threat to Earth or to human civilization. Whatever its true nature, my response should be to maximize the scientific knowledge gained through collaborative observations, not to make defensive preparations. The surveillance hypothesis, in the end, plays a useful role by refining my observational standards and proposing specific tests for artificial intelligence. Even if those tests confirm a natural origin, by thinking like intelligence analysts and not just as astronomers, I develop more advanced techniques for telling the difference between the signs of natural phenomena and those of artificial systems. Whether 3 Atlas is a sophisticated alien surveillance tool or just a fascinating piece of physics, it is teaching me to view our solar system from an external perspective, as an environment that could be analyzed, measured, and comprehended by observers who evolved under different stars. In that light, every meticulous observation I make has a dual function. It advances human understanding and, at the same time, shows the level of technological sophistication that hypothetical aliens might anticipate from our civilization. The watchers, if they are out there, are certainly taking notes. The question is whether we are advanced enough to realize we are being observed and mature enough to observe them observing us in return. Part 11. The Silent Witness. What if 3 Atlas is not collecting intelligence about us, but is instead transmitting information about its creators? This beacon hypothesis changes my interstellar visitor from a spy into a lighthouse, a cosmic landmark proclaiming we existed to any being advanced enough to interpret the message. The idea of inscribed matter is one of the most brilliant methods for interstellar communication ever conceived. Instead of sending out electromagnetic signals that weaken with distance and can be disturbed by stellar interference, advanced societies could encode information directly into the atomic and molecular makeup of physical objects. Such messages would travel at the speed of matter, not light, slower but with flawless accuracy over any distance and time. I consider the benefits of this method. Radio signals from Earth have been spreading into space for about 100 years, but they are already so faint that they would be impossible for our own technology to detect at distances of just a couple of light years. In contrast, physical objects keep their information content forever if they are well preserved. A single artifact the size of a comet could hold the equivalent of every book, movie, and digital file ever made by human civilization. The methods of encoding could be incredibly advanced. Isotope ratios could be deliberately altered to form detectable patterns that communicate mathematical or linguistic data. Crystal lattices could store digital information through specific arrangements of dopant atoms that stay stable for millions of years. Complex organic polymers could contain genetic information, cultural knowledge, or technological plans in sequences similar to DNA, but much more densely packed with information. 3 Atlas offers little support for the beacon hypothesis based on its trajectory alone. Since it does not make a close approach, any message it carries would be aimed at long-term finders rather than immediate recipients. Perhaps the objective is not to communicate with any particular civilization, but to create a galactic archive of information with countless artifacts spread throughout space, waiting for civilizations with sufficient technology to discover and decipher them. This method has significant advantages over scenarios involving direct contact. Messages can be carefully composed without the unknowns and time lags of real-time communication over interstellar distances. Information can be checked, improved, and perfected before being sent. Most importantly, the senders have full control over what they share and with whom, since only civilizations with the right technology and drive would be able to find and understand the messages. From an archaeological standpoint, such beacon objects would be the ultimate form of preserving culture. Human societies have always faced the problem of information being lost over generations. Libraries are destroyed by fire, languages become extinct, and technologies grow outdated. But messages encoded in the structure of atoms and kept safe in the vacuum of interstellar space could remain perfectly intact over geological time. The task of detection becomes immense. However, current spectroscopic methods can identify molecular species and measure isotope ratios with remarkable accuracy. But to recognize artificial patterns, I need to know what I am looking for. Natural processes create their own isotopic signatures through stellar nucleosynthesis, radioactive decay, and chemical fractionation. To tell the difference between natural and artificial patterns requires highly sophisticated analysis and probably some existing knowledge of the encoding techniques used. Microstructural analysis presents further opportunities. Crystalline structures, grain boundary compositions, and microscopic textures might hold information that can only be found through direct sampling and laboratory study. Such fine-scale encoding would be hidden from remote observation, but could preserve massive amounts of data in forms that are stable over cosmic timescales. The philosophical consequences go beyond just storing information to questions about the purpose and morality of sending messages between stars. Why would a society choose to send out information instead of staying defensively silent? What kind of knowledge would be important enough to preserve and send across the galaxy? How should those who receive it react to such findings? One idea involves civilizations on the brink of extinction due to natural disasters, stellar evolution, asteroid impacts, or climate change. Such societies might launch technological time capsules as a form of insurance against complete destruction, in the hope that their knowledge and cultural accomplishments would one day be found by other intelligent beings and kept for future generations. Another scenario imagines advanced civilizations purposely distributing educational materials throughout the galaxy, like cosmic textbooks left for younger societies to find once they reach a suitable level of technological advancement. This method avoids the cultural disruption that direct contact could bring, while still allowing knowledge to be transferred across species and evolutionary histories. The current limits in my ability to detect such messages should not deter me from thinking about their potential existence. Remote sensing gives only a rough idea of an object's composition and structure. The kinds of fine-scale patterns that could encode substantial information are mostly hidden from telescopic observation, whether they are actually there or not. Future missions to return samples from interstellar objects could potentially uncover such encoding through thorough laboratory analysis. Microscopy, mass spectrometry, and crystallographic analysis might find artificial patterns that are completely invisible to remote observation. But such missions are decades away with our current technological abilities and funding limitations. For the time being, 3 Atlas continues to look remarkably ordinary for a comet, despite its interstellar origins and unusual chemistry. Its carbon dioxide-rich composition might just be a result of natural formation processes in a cold stellar environment rather than any kind of artificial encoding. Its morphological changes follow expected patterns based on solar heating and the sublimation of volatiles, without any clear irregularities that would point to artificial control or information content. Nevertheless, the lack of obvious beacon signals does not rule out the possibility completely. The most advanced messages might be crafted to be undetectable until the recipients have the right decoding technologies and theoretical knowledge. I could be looking at a cosmic library without seeing the books on its shelves. Even if 3E Atlas is proven to be entirely natural, it still acts as a kind of beacon, a messenger with information about chemical processes in distant star systems, the dynamics of interstellar matter transport, and the variety of conditions that define planet formation across the galaxy. Every spectroscopic measurement I take adds to my understanding of cosmic evolution and the processes that shape matter through space and time. The universe is always speaking to me through these natural messengers. The question that drives my inquiry is whether some of those messages might be more than just chemical, whether they might contain the deliberate thoughts and intentions of minds that once thought about the same mysteries I consider today. Whether it is natural or artificial, 3E Atlas serves as a reminder that I live in a galaxy where information moves not just as electromagnetic waves, but as matter itself. Cosmic bottles with messages inside, crossing the vast ocean of space, waiting for patient collectors to find out what stories they might have to tell. Part 12. The Universe as a Laboratory. Earth holds a special place in my cosmic vicinity, being the only confirmed biosphere within many dozens of light years. It is a living laboratory where chemistry has arranged itself into self-copying systems of incredible complexity. From an outside view, our planet could be seen as the ultimate scientific chance, a controlled experiment in biological evolution watched from a safe distance. This laboratory hypothesis considers whether 3E Atlas could be part of a long-term observational study of life on Earth. Not an intervention or interference, but a careful scientific watch of evolutionary processes that happen over geological time. The question changes my visitor from a reconnaissance probe or a cultural beacon into something much more subtle, a scientific tool made to understand how life grows on planets like ours. Modern science already sees Earth as a model for habitability through the new field of astrobiology. I analyze our planet's atmospheric makeup, surface chemistry, and biological signs as stand-ins for what I might hope to find on exoplanets orbiting faraway stars. The methods I use to study my own biosphere, spectroscopic analysis of atmospheric gases, watching seasonal changes in vegetation, describing biogeochemical processes, could be easily used by outside observers studying us. But this is where the hypothesis immediately faces big problems based on what I can see. 3 Atlas will not get closer to Earth than 1.6 astronomical units, which is about 250 million kilometers. This distance makes a detailed study of Earth's biological processes practically impossible with any technology I can imagine. Earth would look like nothing more than a pale blue speck. Its biosignatures would only be detectable with the most sensitive atmospheric spectroscopy. For perspective, my most advanced space telescopes can just barely detect the atmospheric compositions of Jupiter-sized exoplanets orbiting stars nearby. Describing the complex atmospheric chemistry that points to biological activity on Earth-sized worlds is still at the very edge of my technological abilities. Even with instruments made just for such observations, if advanced civilizations wanted to study Earth's biosphere in detail, they would have to place their monitoring systems much nearer to our planet. Lagrange point spots, co-orbital positions with Earth, or high-inclination solar orbits would offer much better observation points than hyperbolic interstellar paths that are only in our inner solar system for a few months. This limitation suggests that any experimental monitoring done by 3-Atlas would be on the broader conditions of the heliosphere rather than on specific biological processes. The probe's path samples characteristics of the solar wind, changes in the magnetic field, and cosmic ray environments that affect the atmospheres of planets all over our solar system. Such data could show general conditions for life without needing to get close to any one world. The philosophical context includes competing ideas about how rare complex life is in the universe. The rare Earth hypothesis, put forward by Peter Ward and Donald Brownlee, suggests that while simple microbial life might be common across the galaxy, complex multicellular organisms that need specific planetary and stellar conditions might be extremely uncommon. Earth's biosphere could be a valuable scientific sample worth careful long-term study. On the other hand, the principle of mediocrity suggests that Earth's conditions and biological evolution might be quite common among rocky planets in habitable zones around stars like the Sun. If life is plentiful in the galaxy, then individual biospheres might be less valuable scientifically and less likely to warrant special monitoring missions. Recent findings of potentially habitable exoplanets like Kepler 452b, the worlds of the TRAPPIST-1 system, and Proxima Centauri b suggest that Earth-like planets might indeed be common in my galactic area. This abundance would lessen the scientific reason for a detailed study of any single biosphere, since similar experiments would be happening on countless worlds all over the galaxy. The anthropic principle adds another layer of complexity to these thoughts. Observers will always find themselves in environments that allow for observation. I exist in conditions that let me exist, which tells me nothing about whether such conditions are common or rare in the wider universe. This selection effect makes it hard to judge whether Earth is a typical result of planetary evolution or a remarkable exception that deserves special focus. If the laboratory hypothesis is useful at all, it is not in explaining 3-Atlas in particular, but in making me think about what kinds of observations would actually be surprising. What signs would point to a systematic study instead of natural processes? What patterns would suggest experimental manipulation rather than evolutionary chance? Real experimental interventions might leave behind detectable evidence. The regular introduction of organic compounds with unusual isotopic signatures could possibly be traced through geological records. A systematic change in atmospheric chemistry might appear in ice core data or sediment layers. Even small genetic changes in Earth's organisms might be found through comparative genomics, though telling such interventions apart from natural evolutionary processes would be incredibly hard. More likely, long-term observational studies would focus on describing the conditions of the heliosphere that affect planetary atmospheres and climate systems. Changes in the solar wind, shifts in cosmic ray flux, and fluctuations in the magnetic field. All of these influence atmospheric chemistry and biological evolution in ways that outside observers might want to understand for comparative planetology studies. The ethical aspects of such research are fascinating to think about. How would advanced civilizations balance their scientific curiosity with principles of non-interference? What rules might guide the study of less advanced civilizations? How would they weigh the scientific worth of detailed observations against the dangers of cultural contamination or psychological harm from discovering they are being watched? My own scientific ethics offer some direction here. Modern anthropology and ecology work under strict rules meant to reduce their impact on the subjects they study while getting the most scientific understanding. Observational studies are chosen over interventional experiments when studying complex systems that could be disturbed by direct interference. Similar principles might control interstellar research programs run by civilizations millions of years more advanced than my own. The issues of recognition and respect bring up deep questions about how to respond to confirmed surveillance. Should humanity try to communicate with hypothetical observers? Should I change my behavior knowing I might be watched? Should I deliberately show that I know about potential monitoring to prove my growing scientific sophistication? For now, these are all just speculative questions. Since 3I Atlas continues to act in ways consistent with the physics of a natural comet, its carbon dioxide-rich chemistry shows the conditions of its formation in its parent stellar system, not any clear experimental goal. Its path samples conditions in the heliosphere without getting close enough to Earth for detailed monitoring of the biosphere. Still, the laboratory hypothesis is valuable because it broadens my thinking about the possible reasons for interstellar visits. Not all scenarios of alien contact involve conquest, trade, or direct communication. Some might involve patient scientific study over geological time by civilizations whose research projects last for millions of years. The universe is already running huge experiments in biological evolution on countless worlds across the galaxy. The question that drives my investigation is whether some of those experiments might be watched, recorded, and analyzed by conscious minds, trying to understand the deeper patterns that control the emergence and development of life on a cosmic scale. Whether 3 Atlas is part of such scientific observation or just natural cosmic junk, it reminds me that Earth is part of a larger context of galactic evolution and astronomical processes. I am not a separate observer studying the universe from the outside. I am part of the experiment itself, a temporary arrangement of matter and energy that has gained the amazing ability of self-awareness and scientific curiosity. In that way, every observation I make of 3 Atlas both advances human knowledge and shows the level of scientific sophistication that Earth-based intelligence has reached. I am studying the universe while the universe, through me, studies itself. The laboratory experiment goes on, and I have become both the subjects and the scientists in the great investigation of cosmic evolution. Part 13. Other Suspects in the Sky. To grasp the importance of 3 Atlas, I must situate it within the expanding list of interstellar travelers that have visited our solar system in recent times. Each object presents a unique narrative showcasing the variety of materials and phenomena that define planetary systems throughout my galactic vicinity. One-Eye, Oumuamua, continues to be the most mysterious item in this group. Found on October 19, 2017, this cigar-shaped object showed non-gravitational acceleration without any visible evidence of outgassing, a behavior that defied all models of natural comet and asteroid physics. The Spitzer Space Telescope's infrared observations found no thermal emissions from sublimating volatiles. Nevertheless, something was propelling Oumuamua faster than gravity alone could explain. The debate led to several competing theories, each with considerable merits and flaws. Marco Michel's team, in a publication in Nature, precisely measured the acceleration but could not determine its cause. The hydrogen iceberg theory suggested invisible H2 sublimation, but molecular hydrogen ice is not expected to last for millions of years in the interstellar radiation field. The nitrogen iceberg theory proposed pieces of Pluto-like crusts, but necessitated implausibly massive parent bodies to generate kilometer-sized fragments. Abraham Loeb and Shmuel Bialy's radiation pressure theory provided a compelling alternative. If Oumuamua had an exceptionally low density and a large surface area, essentially a thin sheet, then solar radiation pressure by itself could account for the acceleration observed. This light sail-like explanation was both testable and contentious, igniting debates that persist today about the line between natural occurrences and artificial constructs. 2. Why Borisov offered a striking contrast upon its discovery by amateur astronomer Gennady Borisov on August 30, 2019. This object acted like a model comet, exhibiting strong outgassing, a significant coma, and clear tail formation as it neared perihelion. Observations from the ALMA radio telescope indicated unusually high levels of carbon monoxide, among the highest ever recorded in any comet, pointing to its formation in extremely frigid areas of its home star system. Monitoring by the Hubble Space Telescope through 2020 captured minor fragmentation events, with small fragments detaching from the main nucleus in a manner entirely consistent with natural thermal stress and structural fragility. These observations gave me my first in-depth look at how interstellar comets react to solar heating, setting a baseline for what to expect from natural versus artificial activity. Now, 30 Atlas contributes a third piece of data to this developing picture. Its chemistry, dominated by carbon dioxide, is distinctly different from both Oumuamua's seeming absence of volatiles and Borisov's abundance of carbon monoxide. This chemical variety implies that interstellar objects come from a broad spectrum of formation settings and stellar system conditions across the galaxy. But the narrative does not conclude with these three confirmed interstellar objects. In 2022, the U.S. Space Command released a memorandum stating with 95% confidence that a meteor picked up by Department of Defense sensors on January 8, 2014, had come from outside our solar system. This interstellar meteor, named Iman, is said to have entered Earth's atmosphere at roughly 60 kilometers per second and detonated over the Pacific Ocean near Papua New Guinea. The assertion triggered a heated scientific discussion. Harvard's R.V. Lobo led expeditions to retrieve pieces from the ocean floor, announcing the finding of metallic spherules with unusual compositions that could be the first recovered samples of interstellar material. However, these assertions are still disputed within the scientific community, with objectors claiming that the initial velocity readings were not enough to confirm an interstellar origin and that the recovered spherules might be terrestrial contamination or standard meteoritic substances. Other potential interstellar meteor candidates have been put forward, including IM-2, detected in 2017, but these objects pose even greater observational hurdles. Unlike the large, long-lasting objects that astronomical surveys can monitor for months, interstellar meteors offer only a few seconds of observational data before they break up in Earth's atmosphere. The pattern that comes from these varied objects makes any simple theory of artificial origin difficult. If extraterrestrial civilizations were sending probes to my solar system, I might anticipate some uniformity in design principles, chemical makeup, or behavioral traits. Instead, I see remarkable diversity that is more easily explained as remnants from various stellar systems with different formation circumstances. Oumuamua's acceleration anomaly is still truly baffling, but it is an exception rather than part of a consistent trend. Borisov's high carbon monoxide levels reflect natural chemistry in cold protoplanetary settings. 3 Atlas's carbon dioxide abundance points to yet another formation environment, perhaps nearer to the CO2 ice line in its original system. This variety actually supports the case for natural origins while offering fascinating glimpses into planet formation processes throughout the galaxy. I am directly observing samples of materials that formed in stellar systems with different temperature profiles, chemical makeups, and evolutionary paths. Each object acts as a cosmic core sample, showing conditions that existed billions of years ago in remote parts of space. The upcoming Vera Rubin Observatory is set to transform my understanding of these phenomena by greatly increasing the rate at which interstellar objects are detected. Current surveys find maybe one interstellar visitor each year, but Rubin's wide field capabilities could uncover dozens annually. This statistical enhancement will aid in distinguishing between natural variety and possibly artificial patterns, while also furthering my knowledge of galactic ecology and the movement of matter between stellar systems. For the study of technosignatures, the diversity of interstellar objects presents both difficulties and opportunities. The difficulty is in identifying artificial signs against a backdrop of natural chemical and morphological differences. The opportunity arises from creating ever more sophisticated analysis techniques that can differentiate between natural and artificial processes with a high degree of certainty. 3 Atlas benefits from this expanding comparative framework. I now know that interstellar objects can show unusual chemistry, Borisov's CO richness, unexpected behavior, Oumuamu's acceleration, and diverse compositions that reflect their formation environments. Against this backdrop, 3I Atlas seems relatively normal, a comet with a somewhat unusual but not unprecedented chemistry, following predictable behavior patterns as solar heating causes volatile sublimation. Yet each new discovery broadens my understanding of what is possible in the world of interstellar debris. The universe keeps surprising me with objects that challenge my models and assumptions about natural processes. Whether any of these surprises will ultimately turn out to involve artificial rather than natural phenomena is still an open question. It is one that demands careful observation, strict analysis, and the intellectual humility to tell the difference between what I hope to find and what nature actually shows. The sky above me holds messages from all over the galaxy, chemical signatures of distant worlds, physical remnants of ancient stellar processes, and maybe, just maybe, the technological artifacts of civilizations that mastered space travel long before Earth had even formed. My job as a scientist is to read these messages with care, to separate the signal from the noise, and to stay open to discoveries that might challenge my most fundamental assumptions about life and intelligence in the universe. Part 14. The Supernatural Layer. Throughout human history, comets have acted as cosmic punctuation marks in the narrative of civilization. They have been seen as harbingers of change, omens of doom, and celestial messengers that required interpretation by those who observed their otherworldly displays. This cultural layer of creating meaning came long before scientific understanding, and its psychological remnants still shape how I respond to unusual objects in the sky. The assassination of Julius Caesar in 44 BCE coincided with the appearance of a brilliant comet, which Romans saw as the dictator's soul rising to join the gods. This Julian star turned into a potent political symbol used by Caesar's heir Octavian to validate his claim to power. The comet was featured in artwork, on coins, and in architectural designs throughout the Roman Empire, changing a natural astronomical event into a key part of imperial propaganda. Ancient civilizations kept surprisingly detailed records of comet appearances. Babylonian astronomers monitored Halley's Comet for more than 2,000 years, noting its regular returns with enough accuracy to retroactively identify historical sightings that were not recognized as the same object until modern orbital calculations showed their shared identity. Chinese court astronomers documented comets as signs of dynastic health, interpreting their brightness, duration, and tail features as messages about imperial authority and divine favor. Medieval European chronicles are filled with stories of comets appearing at the same time as battles, plagues, political turmoil, and natural disasters. The Great Comet of 1066, now known to be Halley's Comet, showed up just months before the Norman conquest of England and was later shown in the Bayeux Tapestry as a sign of Harold Godwinson's loss at the Battle of Hastings. The scientific revolution slowly substituted supernatural interpretation with physical comprehension. Edmund Halley's calculation of cometary orbits proved that these objects adhered to predictable gravitational laws rather than divine caprice. Spectroscopic analysis uncovered their chemical makeup: water, carbon dioxide, carbon monoxide, and other volatile substances sublimating due to solar heat. Space missions to comets like Giotto's flyby of Halley in 1986 gave direct measurements of their nucleus composition and internal structure. Yet the emotional impact remains. Impressive comets like Hale-Bopp in 1997 and Neowise in 2020 sparked global public interest that went beyond purely scientific curiosity. Social media intensifies this phenomenon, with stunning comet photos spreading quickly through networks that celebrate natural beauty alongside conspiracy theories and supernatural beliefs. Modern myth-making is susceptible to the same psychological lures that influenced ancient observers. Atypical observations are exaggerated through biased reporting and confirmation bias. Anti-tail formations, fragmentation events, and unusual chemical compositions lead to speculation about artificial interference or extraterrestrial visits. The line between a valid scientific hypothesis and wishful thinking gets hazy when dealing with phenomena that challenge my current understanding. 3 Atlas is at this fascinating crossroads of ancient wonder and modern precision. Its interstellar origin makes it, quite literally, a messenger from another star system, a poetic truth that is as compelling as any mythological story. The carbon dioxide-rich chemistry found by the James Webb Space Telescope provides factual information about conditions in distant stellar environments that my ancestors could never have dreamed of accessing. But I must be careful to distinguish between optical illusions and physics, between normal behavior and genuinely anomalous signs. The same pattern recognition that helped my ancestors survive by finding meaningful signals in chaotic environments can lead to false positives when applied to astronomical phenomena, faces in clouds, intent in randomness, and design in natural processes. These cognitive biases demand constant watchfulness in scientific research. Advanced image processing and statistical analysis are tools to lessen these psychological effects. Machine learning algorithms can spot subtle patterns in spectroscopic data while avoiding the pareidolia that affects human visual interpretation. Automated survey systems find and categorize thousands of objects without the emotional attachment that might lead human observers to see what they want to find instead of what is actually there. The responsibility is especially great when I communicate scientific findings to the public. Headlines that sensationalize anti-tail formations or unusual chemistry can spread misinformation faster than corrections can catch up. The act of balancing the communication of genuine scientific excitement with the avoidance of misleading speculation demands constant care with language, context, and standards of evidence. 3 Atlas is a true wonder, no matter what its final explanation turns out to be. This object, formed in another stellar system billions of years ago, survived the long journey through interstellar space and reached my solar system at the very moment when human technology was advanced enough to study it in detail. The observations from the James Webb Space Telescope offer my first high-resolution spectroscopic analysis of an interstellar visitor before it gets to perihelion, a scientific opportunity that would have been impossible just a few years ago. The timing seems almost preternatural in its convenience, but it is the result of natural astronomical processes meeting human technological progress rather than any divine plan or alien scheduling. Survey telescopes like Atlas find interstellar objects when they are there and when my detection capabilities are sensitive enough. Advanced spectroscopic instruments like JWST reveal chemical compositions when their observation windows match funding choices made years before. This story of coincidence and discovery has its own kind of magic, the magic of the scientific method revealing hidden patterns in natural phenomena. Whether 3 Atlas is proven to be entirely natural or to have unexpected artificial signs, it stands as a testament to human curiosity and technological skill. I can now analyze the chemical makeup of objects that came from stellar systems dozens of light-years away, detecting molecular species and isotope ratios with a precision that would have seemed miraculous to ancient astronomers. The universe offers enough real wonder to inspire awe without needing supernatural explanations or alien involvement. Stellar nucleosynthesis creates the elements that make up my body over billions of years of cosmic evolution. Gravitational dynamics send debris between star systems on paths that sometimes bring distant worlds within the range of my telescopes. Chemistry and physics work according to principles so elegant they can predict the behavior of comets while showing the fundamental unity behind apparent diversity. Sometimes the most profound magic is not in finding that wizards exist, but in understanding how nature can perform tricks so sophisticated they inspire centuries of supernatural interpretation. 3 Atlas continues this legacy, a cosmic illusion that challenges my assumptions while rewarding careful observation with insights into processes that shaped matter across the galaxy long before Earth had even formed. The ancient observers were right about one thing. Comets do bring messages from the heavens. They were wrong only about the nature of those messages, which turned out to be far more wonderful than any mythology could have imagined. Chemical signatures of stellar evolution, gravitational dynamics of planetary formation, and physical processes that link my local environment to the wider cosmos in ways that make any human idea of divine intervention seem small. Part 15. The Final Ambiguity. I now come back to the main question that has steered this inquiry. If 3I Atlas was created, by whom, for what reason, and why at this time? After looking at the evidence from various angles, surveillance, communication, seeding, reconnaissance, archaeology, I find myself facing not clear answers, but a richer understanding of the uncertainties that make this question so fascinating. Let me recap what I have gathered through careful observation. 3I Atlas is on a hyperbolic path with an eccentricity of about 6.08 and a velocity at infinity of 57 to 61 kilometers per second, which clearly confirms its interstellar origin. It will not get closer to Earth than 1.6 to 1.8 astronomical units, which eliminates any scenarios of direct interaction. Spectroscopy from the James Webb Space Telescope shows a chemistry dominated by carbon dioxide, with unusual CO2 to water ratios that suggest it formed near a CO2 ice line in its home stellar system. Observations from Hubble reveal a typical comet appearance, with the development of a coma and a dust tail that is consistent with the natural sublimation of volatiles due to solar heating. The size is limited to an upper boundary of roughly 5.6 kilometers, though the nucleus could be much smaller. No fragmentation has been confirmed as of the latest observations, although thermal stress near perihelion might cause breakup events that are common in natural comets. The trajectory planning, if it is artificial, seems less than ideal for a specific reconnaissance of Earth, but sufficient for sampling the heliosphere or for a general characterization of the solar system. This leaves me with 2 main interpretations, both of which are internally consistent but demand different levels of proof. Interpretation A posits a natural origin. 3 Atlas is a comet that was ejected from a stellar system with an unusual chemistry, possibly forming closer to the CO2 ice line than is typical in my solar system. Its behavior under solar heating follows predictable patterns based on the sublimation of volatiles and the release of dust. The chemical variety among interstellar objects is a reflection of the range of formation environments throughout the galaxy. Interpretation B suggests an artificial origin. 3 Atlas is a disguised probe that uses natural comet physics to hide advanced instrumentation. Its chemical makeup serves as thermal insulation and radiation protection for its internal systems. Outgassing provides a natural cover for any artificial emissions or propulsion effects. The trajectory allows for the sampling of heliospheric conditions, which is valuable for understanding the characteristics of my solar system. The current evidence leans more strongly towards interpretation A, but interpretation B has not been disproven by the available data. The key observations that could differentiate between these 2 possibilities will come during the perihelion passage around October 30th, 2025, and the subsequent monitoring through December 2025, when 3I Atlas becomes visible again after passing the Sun. What findings would definitively alter my assessment? Repeatable non-solar modulations in the production of dust or gas would point to internal activity cycles that are not consistent with natural heating patterns. The detection of refined metals, artificial compounds, or unusual crystalline structures would indicate manufacturing processes rather than natural condensation. Anomalous line emissions at wavelengths that do not correspond to known molecular transitions could be a sign of technological systems. The most compelling evidence would be encoded signals, patterns in the timing of outgassing, the composition of dust grains, or electromagnetic emissions that convey information rather than just reflecting physical processes. The contributions of Abraham Loeb to this field should be acknowledged, whether his specific hypotheses are proven right or wrong. The radiation pressure theory for Oumuamua's acceleration, though contentious, led to testable predictions and encouraged a more sophisticated analysis of interstellar objects. His broader framework for technosignature research, which focuses on distinguishing artificial from natural phenomena through strict observational criteria, moves the field forward even when it is applied to objects that are ultimately found to be natural. The scientific ethos demands that I maintain extraordinary standards of evidence while also staying open to discoveries that challenge existing paradigms. I must avoid both the uncritical acceptance of exotic theories and the automatic dismissal of possibilities that seem improbable based on my current understanding. The universe has consistently surprised me with phenomena that went beyond my theoretical predictions, from quantum mechanics and dark energy to extremophile organisms that thrive in environments once thought to be uninhabitable. My responsibility in communicating with the public is particularly vital, given the potential for misinformation on topics that involve possible extraterrestrial intelligence. Clearly identifying speculation as such, updating my assessments as new peer-reviewed findings are released, and keeping a clear distinction between evidence and inference are essential to prevent the spread of unfounded claims that could harm legitimate scientific research. The observations from the James Webb Space Telescope, published in preprint form, are preliminary findings that need peer review and confirmation before I can draw any firm conclusions. As solar heating increases during 3I atlases approach to perihelion, more advanced spectroscopic analysis could uncover molecular signatures that either confirm natural formation scenarios or point to something more complex. The metaphor of a locked door in space perfectly describes my current situation. I can see the door's external features, its size, composition, trajectory, and surface properties, but I cannot yet tell if it opens to natural processes or to artificial intelligence. Sometimes the most profound discoveries come not from finding the key that opens such doors, but from learning to ask better questions about what I might find on the other side. The search for technosignatures in objects like 3I Atlas has valuable scientific purposes, regardless of the final answers. It pushes me to develop more advanced analysis techniques, to consider alternative explanations for unusual observations, and to uphold rigorous standards of evidence when faced with extraordinary claims. Even confirming a natural origin enhances my understanding of interstellar debris, the processes of planetary formation, and the chemical diversity that is characteristic of stellar systems throughout the galaxy. As I near the critical observation period in late 2025, a number of ground-based and space-based telescopes will monitor 3 Atlas with unprecedented accuracy. The James Webb Space Telescope, the KEK Observatory, the Very Large Telescope, and the Hubble Space Telescope will all track its evolution as solar heating leads to increasingly intense activity. These coordinated observations are my best chance to distinguish between natural and artificial explanations for this mysterious visitor. The outcome will advance human knowledge, no matter which interpretation turns out to be correct. If 3A Atlas is natural, I will gain insights into chemical processes in distant stellar systems and the mechanisms that move matter between stars. If it contains artificial elements, I will face the profound challenge of recognizing and responding to evidence of extraterrestrial intelligence. In either scenario, the investigation is a prime example of the scientific method at its most sophisticated. Careful observation, rigorous analysis, and intellectual humility in the face of cosmic mysteries that are far beyond human experience. I remain a patient observer, following the evidence wherever it may lead, ready for discoveries that could change my understanding of life and intelligence in the universe. The silence between the stars might still contain voices I have not yet learned to hear. But first, I must perfect my ability to tell the difference between the whispers of physics and the possibility of something more. Something that chose to visit my solar system disguised as a dirty snowball from the stars, carrying secrets I am only just beginning to learn how to read. The locked door drifts past me at 61 kilometers per second. Whether it opens onto natural wonders or artificial marvels, the universe continues to teach me patience, precision, and the profound humility that comes from realizing how much I still have to learn about the cosmos I inhabit.